All right, our next speaker this afternoon is Hahn. Isa joined us from Pomona this summer, and she's been working with Henrique, and she'll tell us today about her project investigating photometric ages and metallicities of subgiants.
Thank you, Gwen, and thank you everyone for being here today. So to start off, stellar ages are an important parameter in astronomy. They tell us about the evolution of not just the stars themselves, but also of the galaxies they live in. However, they are notoriously hard to get. And subgiants in particular are special in that we can determine their ages a little bit easier. This is because they have a very unique evolutionary standpoint. They exist in this really tiny area on the HR diagram, just between main sequence turnoff and the red giant phase. And they have a scaling relationship between their luminosity to their core mass, which scales to their stellar mass, which then scales to their main sequence lifetime. And because they're in this little spot here where they're just leaving the main sequence, we can use that relationship to determine their ages. I have this little relationship here showing the relative dependence, but the exact dependence is a function of luminosity, temperature, metallicity, and age. So my project this summer is based off of a study by Notoff et al. And what they did in this study was they determined the ages and metallicities for around 420,000 subgiants. They used isochrones to do this, which uses stellar models and interpolates them with derived parameters, and they input solely photometric data. This here is the results of their study. And as you can see, there's a pretty strong relationship right here between age and metallicity for metal rich stars. However, for metal poor stars, there's not really a clear pattern, and there should be a pattern there. So this kind of begs some questions of where is the pattern and why isn't it showing up? Is it because of the data? Was it not enough data? Is it the kind of data? And so that's sort of what we've been investigating this summer. I wanted to talk a little bit about the data specifically, photometry versus spectroscopy. So photometry measures brightness in magnitudes in specific filters. Here I have this image from SkyMapper, and it shows 3 different photometric bands and the wavelength regions that they cover. You can use a combination of different filters to cover an entire black body and derive chemical abundances from that. However, it's indirectly measuring chemical abundances, so it's not as accurate. However, it is readily available in a lot of existing surveys, so it's a little easier to get. On the other hand, spectroscopy spreads light into individual wavelengths using an instrument called a spectrograph. This is an example of the solar flux atlas, which shows some spectra from the sun. And as you can see, there's different lines at different chemical transitions. And that is because spectroscopy directly measures chemical abundances of different elements. So that's really cool, but it's pretty hard to get. In order to get this amount of information, you need really high resolution and low noise. So it needs to be directly observed if we want to actually work with the data. So to reiterate, photometry contains less information, but it's easier to get, whereas spectroscopy contains more information, but it's a little bit harder to get. So I looked at 2 specific stars from the Notoff study this summer. They were selected only because they were metal poor. And these are the results that the Notoff study found for those stars using only photometric data. So the first star has a metallicity of -1.02 and an age of 11.15 gigayears, and the second star had a metallicity of -1.13 and an age of 6.3 gigayears. And we wanted to know how adding spectra would change these results. My process this summer is as follows. First, I obtained the spectra from the Mike spectrograph. The spectra for the first star was observed by my advisor, Henrique, and the second star was observed by John Galarza. Then I put this spectra in Spectroscopy Made Harder, and I use this to measure the equivalence width. This is a little diagram kind of showing what equivalence width is. This represents the spectra here, and the equivalence width is just the width of a rectangle that contains the same area as the value underneath the curve, and we can use that to determine chemical abundances. This is a screenshot of Spectroscopy Made Harder, which is the program I use to actually analyze the spectra, and this is one spectral line that I looked at. In the black, you can see the spectra from my star, and then the red is a fit of that specific line. And this is how I was able to determine the equivalence widths down here. After that, I use those equivalence width values to measure stellar metallicity. Stellar metallicity relates to equivalence width through this relation. It's a direct relationship. Here's equivalence width, and here's the chemical abundance of any particular element that you were looking at. We looked at iron because iron is often used as a tracer element to determine the metallicity of stars. After that, I gathered some additional photometric and astrometric data. I got my photometric data from Galax, Gaia, 2MASS, WISE, SkyMapper, and Tycho 2 from Hipparcos. My distances were from Baylor Jones 2021. I also got parallax from Gaia, and then I was able to get extinction from stylism. After that, we adjusted data inclusions based on flags that were included in the photometric data, and they basically tell us how reliable this data is. And then I performed an isochrones fitting. After that, I repeated iterations until I was able to identify the best fit, and from that, I determined an age. Here is an example of one of my isochrones iterations. As you can see, there are a lot of variables. We input a lot of data, and so I did this, a little zoomed in section so we can actually see what's going on, and I can explain it a little bit. So in the blue, these lines represent the values that I input, so mostly photometric data that I found. And then the gray is the posterior that isochrones has. And we have a pretty good match between the posterior from isochrones and our inputted data, which is really good. That means that the model is a good match of our star. And I know some of you might be looking at this difference here, but I wanted to point out that it's actually really tiny. This scale right here is very small, and this difference is within the bounds of our error on that measurement, so it's still a good fit. Then I was able to get derived parameters from isochrones. So we derived the surface gravity, the metallicity, the mass, and the age. And here are my numerical results. So for my first star, we found a metallicity of -1.22 and an age of 13.42 gigayears. And then I did the same thing for the second star, and we found a metallicity of -0.44 and an age of 4.84 gigayears. I wanted to show a direct comparison between our study and the Notoff study so we could talk about the differences between them. So mainly, the first thing that jumps out is that there's a really big difference in the ages and metallicities between these stars. And that is because we had more data to determine our metallicity. We use spectroscopic data, which gives more accurate metallicities than photometric data. But there was also an issue with the alpha enhancement. In our study, the model atmosphere that we use to determine metallicity accounts for alpha enhancement, but the metallicities that were determined in the Notoff study don't account for alpha enhancement, so this is also likely driving that difference. And the difference in metallicity is what drives the difference in age. I also wanted to point out that we have much smaller errors on our study, and that is just because the method that we use to get our metallicities is a lot more accurate, so there's less error in that regard. And for the second star in particular, the difference is a little bit bigger. The Notoff study thought that it was metal poor and older, and we found it to actually be more metal rich and younger. And this is because of the extinction. The extinction used in the Notoff study was from a different source than our extinction. However, the extinction value that we use actually matches the model produced by isochrones better, and so it's more accurate. So in conclusion, subgiants have a luminosity to age relationship that we can utilize to determine their ages. We found a significant disagreement between our study with spectral and photometric data and that by Notoff, which just used photometric data. From this, we can conclude that adding spectroscopically inferred metallicities actually increases the reliability and accuracy of age inferences. And it puts lower limits on the photometrically determined ages from the Notoff study. Since they determined these ages for 420,000 stars, obviously they wouldn't be able to do this intense analysis for all of them, but that means that maybe there's sort of like a bottom limit to how accurate those ages are, like maybe after a certain metallicity, once you get into the metal poor population, those ages just aren't as accurate. And that's all I have for you. Thank you.
I think this is very nice. You mentioned that there are two differences between your and Notoff study, that you added spectroscopy, but also used a different extinction map. And
Yeah.
so I was just wondering, because in principle, you could employ the extinction map on all of the, for whatever, how many hundreds of thousands of stars.
Yeah.
Do you have a sense of kind of how much would that improve the original Notoff study?
I think it was more for this specific star because we kind of had a hard time getting the extinction for this. Like the error was just pretty large and it's kind of unclear. But I think for this star that we analyzed, for example, the extinction was pretty similar to that found in the Notoff study. So I don't know if it would make that much of a difference for our sample sizes as a whole, but it did make a difference for this particular star.
Thanks.
The first one is really old. Is that
Yeah.
common?
No.
Like, is this the oldest one or
Yeah,
you know?
it's the oldest star that I've ever seen.
That is really weird and
Yeah.
cool. Thank you.
Thank you.
Hey, so this is really cool. And as someone who uses SMHR, I understand this is a lot of work. So well done. Going through all of those lines. It's like hundreds of lines. So well done. Yeah, I have a question about this metal poor star. So that is an incredibly old age for something that I would say is actually that metal rich. So
Yeah.
do you have an idea where this star is in the galaxy?
We don't. I mean, I don't. Henrique might. That wasn't something.
Yeah, is it like is it a disc? Is it in the bulge?
No, it's the inner halo stuff.
Inner halo for those online. Okay, thank you.
All right, let's thank Isa again.